Have you ever wondered how network switches prevent those catastrophic broadcast storms that can bring an entire network to its knees? The answer lies in a protocol that's been quietly working behind the scenes for decades. Today, we're diving into STP, the Spanning Tree Protocol. By the end of this video, you'll understand what STP is, why it's essential, and how it actually works. Let's get started. Let's start with a scenario. Imagine you have three switches connected in a triangle topology: SW1, SW2, and SW3. This setup gives us redundancy, which is great for network reliability. If one link failed, traffic can still flow through an alternate path. But here's where things get problematic. Let's say SW1 sends out a broadcast frame to all its ports. Watch what happens. SW2 and SW3 receive this broadcast and then forward it out all their ports, including back to each other. SW2 broadcasts to SW3, SW3 broadcasts back to SW2, and both broadcast back to SW1. Then the process repeats and repeats and repeats. This creates what we call a broadcast storm, an infinite loop where frames circulate endlessly through the network. The challenges are significant. Broadcast storms consume all available bandwidth. MAC address tables become unstable as switches see the same addresses coming from multiple ports. Switch CPU utilization skyrockets trying to process all these duplicate frames. Without intervention, this redundant network that was supposed to provide reliability actually creates chaos. So how do we fix this? Enter the Spanning Tree Protocol, our hero. STP solves this problem elegantly through two key mechanisms. First, STP enables switches to become aware of other switches in the network using special frames called BPDUs, Bridge Protocol Data Units. Think of BPDUs as hello messages that switches use to discover and communicate with each other. Second, STP builds a loop-free environment by temporarily blocking traffic on redundant ports. Look at the diagram. You'll notice SW2 and SW3 now have interfaces marked /1 that are in a blocking state. By strategically blocking certain ports, STP prevents loops while still maintaining those redundant links as backups. This is the beauty of STP. We get redundancy without the loops. If a link fails, STP automatically recalculates and can unblock those backup ports within seconds. Now, STP isn't just one protocol. It's evolved over the years. Let me walk you through the family tree. We started with 802.1d, the original specification that laid the foundation. Then came PVST, per VLAN spanning tree, a Cisco enhancement that runs a separate spanning tree instance for each VLAN. PVST Plus improved on this, followed by RSTP, Rapid Spanning Tree Protocol, which dramatically reduced convergence times from 30 to 50 seconds down to just a few seconds. Finally, we have MST, Multiple Spanning Tree, which groups multiple VLANs into instances for better scalability. For this video, we'll focus on the fundamental concepts that apply across all these versions. Before we go further, let's nail down some essential terminology. These three concepts are the foundation of how STP works. First up, the root bridge. This is the most important switch in your Layer 2 topology. Think of it as the anchor point or the reference point for all STP calculations. Every spanning tree has exactly one root bridge, and all switches calculate their paths relative to this route. Here's what makes it special. All ports on the root bridge are in forwarding state. None of them are blocked, because by definition, any path through the root bridge cannot create a loop. Next, BPDUs, Bridge Protocol Data Units. These are the network packets that switches use to communicate topology information. There are two types: configuration BPDUs, which identify the root bridge and contain topology change information, and topology change notification, or TCNs, which alert the network when the topology changes. Finally, system priority. This is a 4-bit value that indicates a switch's preference for becoming the root bridge. The default value is 32,668. Here's the key rule. Lower is better. A switch with priority 4096 will win over one with 32,668. Let's continue with 3 more critical terms. The system ID extension is a 12-bit value that correlates to the VLAN number. When you combine the system priority and the system ID extension, you get the bridge priority for that specific VLAN. For example, if you have priority 32,668 and VLAN 1, your bridge priority becomes 32,669. That's 32,668 plus 1. The root bridge identifier uniquely identifies the root bridge. It's a combination of 3 components: the root bridge's MAC address, its system ID extension, and its system priority. This identifier is included in every BPDU, so all switches know exactly which switch is the root bridge. Similarly, the local bridge identifier uniquely identifies each individual switch using that same combination: the local switch's MAC address, its system ID extension, and its system priority. This helps switches distinguish themselves in BPDU exchanges and root bridge elections. STP uses 3 critical timers to maintain network stability. Think of these as the heartbeat and safety mechanisms of the protocol. The hello timer determines how often the root bridge sends out BPDUs. By default, this is every 2 seconds. It's like a heartbeat. I'm still here. I'm still the root bridge. The forward delay timer controls how long a port stays in the listening and learning states. Default is 15 seconds each, so that's 15 seconds listening, then 15 seconds learning, a total of 30 seconds before a port can forward traffic. This delay is crucial because it gives the network time to stabilize and prevent temporary loops during topology changes. Finally, the max age timer determines how long a switch waits for BPDUs before assuming the root bridge has failed and triggering a topology recalculation. The default is 20 seconds. These timers work together to balance network stability with convergence speed. Now let's talk about the different roles ports have in STP. Understanding these roles is key to understanding how STP builds its loop-free topology. First, the root port, shown in green on our diagram. This is the port that connects to the root bridge or provides the best path upstream towards the root bridge. Every non-root switch has exactly one root port. Think of it as the path home to the root. Next, designated ports, also shown in green. These ports receive and forward BPDU frames to downstream devices and switches. Each network segment has exactly one designated port, the one that provides the best path to the root bridge for that segment. Finally, blocking ports, shown in orange. These ports are not forwarding traffic because doing so would create a loop. But here's the important part. They're still listening to BPDUs. If the topology changes, these ports can quickly transition to forwarding. Notice in our diagram how SW2 and SW3 each have one blocking port on interface /1. This prevents the loop while maintaining redundancy. And finally, let's walk through the 5 states every port transitions through in 802.1d STP. This is often tested in certification exams, so pay close attention. State 1, disabled. The port is in administrative shutdown. It's not participating in STP at all and won't forward any traffic. State 2, blocking. The port is enabled, but it's not forwarding traffic to prevent loops. However, it still is receiving BPDUs from other switches. The switch doesn't modify its MAC address table in this state. It's just listening for topology information. State 3, listening. The port has transitioned from blocking and can now send or receive BPDUs. It still cannot forward network traffic, and the duration of this state correlates to the STP forwarding time, 15 seconds by default. State 4, learning. The port can now modify the MAC address table with any network traffic it receives. This helps the switch prepare for forwarding by learning which devices are on which ports. It still doesn't forward traffic yet, but BPDUs continue to flow. This state also lasts 15 seconds. Finally, state 5, forwarding. Finally, the port can forward all network traffic and update the MAC address table as expected. This is the normal operational state for ports that are part of the active spanning tree topology. Remember, going from blocking to forwarding takes approximately 30 to 50 seconds in traditional 802.1d, 15 seconds in listening, 15 seconds in learning, plus any additional convergence time. This is why STP was developed, to dramatically reduce these convergence times. And there you have it,